In the depths of our world's oceans, a giant, invisible force is at work. This force, known as the thermohaline circulation, acts like a conveyor belt, moving heat, nutrients, and dissolved gases across the globe. But how does it work, and why is it so critical to our planet's climate? Let's dive in and explore this fascinating phenomenon. Thermohaline circulation, a term derived from thermo for temperature and halin for salt content, forms a global network of underwater currents, transporting nearly 100 times the volume of the Amazon River. Unlike wind-driven surface currents, this system is primarily powered by differences in water density, which vary with temperature and salinity. It takes a single water molecule approximately 1,000 years to complete this circuit, creating what we call the Great Ocean Conveyor Belt. The comprehensive understanding of thermohaline circulation as a planetary scale phenomenon emerged largely through the pioneering work of oceanographer Wallace Broecker in the 1980s. Broecker's research revolutionized our understanding of how ocean currents influence climate, challenging the previously held notion that atmospheric processes alone drove climate change. This highlighted the ocean's role as an active architect of global climate patterns. The process begins primarily in the North Atlantic near Greenland and Iceland. Here, surface water cools dramatically in winter, and as sea ice forms, salt is expelled into the surrounding water, increasing its density. This cold, saline water becomes heavier than the water beneath it and sinks to great depths, a process oceanographers call downwelling. As these deep currents move through the world's ocean basins, they gradually warm and become less dense, eventually rising back to the surface in upwelling zones. The physical forces driving this circulation are remarkably delicate. The density differences that power the entire global conveyor can be measured in fractions of a percent. Yet these subtle variations generate sufficient pressure gradients to move enormous volumes of water across vast distances. The deep currents typically flow at speeds of only a few centimeters per second, slower than a garden snail. Still, their persistence and volume result in transport capabilities that dwarf all of Earth's rivers combined. Thermohaline circulation serves as Earth's climate regulator in poorly understood ways. It redistributes nutrients throughout the oceans and influences the carbon cycle by absorbing atmospheric CO2 in some regions and releasing it in others, effectively acting as a carbon sequestration system. Beyond temperature regulation, deep waters are rich in phosphates, nitrates, and other elements essential for marine life, creating some of the planet's most productive fishing grounds. Climatologists are increasingly concerned about the potential for anthropogenic climate change to disrupt this system. The Greenland ice sheet is melting at an accelerating rate, reducing the salinity of the North Atlantic. Since 1950, scientists have measured a 15% slowdown in Atlantic meridional, overturning circulation, AMOC, the Atlantic portion of the thermohaline system. A complete shutdown of AMOC would drastically alter global climate patterns, potentially cooling Europe, while shifting tropical rainfall patterns that billions depend on for agriculture. Recognizing the critical importance of thermohaline circulation, scientists have deployed sophisticated monitoring systems across the world's oceans. These include the Rapid Array, which continuously measures temperature, salinity, and current velocity to track the strength of the AMOC. Satellite measurements complement these in situ observations by tracking subtle changes in sea surface height, temperature, and salinity patterns that indicate shifts in deep ocean circulation. The thermohaline circulation, or the Great Ocean Conveyor Belt, is a powerful yet delicate system that shapes our planet's climate. Its discovery revolutionized our understanding of the ocean's role in climate regulation, and continued monitoring will be crucial for predicting and mitigating the impacts of climate change. As our knowledge of this remarkable system grows, we are reminded of the intricate interconnectedness of our planet's systems and the importance of preserving their balance for our collective future. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated.